In this video, I want to introduce the idea of a power series. But before I do that, we need to review some improper integrals. So let's consider the integral from 1 to infinity of x to the p dx. For what values of p does this integral converge? Well, first off, let's check p equals 1. If p equals 1, I've got the integral from 1 to infinity of 1 over x. This is natural log of x when I integrate, and natural log of infinity is infinity, so this diverges. So from now on, I'm going to assume that p does not equal 1. You'll see why in a second. So I have the integral from 1 to infinity of 1 over x to the p dx. Since this is an improper integral, I need to take a limit as b goes to infinity, integrate from 1 to b of x to the negative p dx. I went ahead and wrote it as x to the negative p, so it would make integrating easier in the next step. Integrating x to the negative p, I add 1, divide by what I get. So I get x to the 1 minus p over 1 minus p. Limit as b goes to infinity, that's taken from 1 to b. Oh, my b got chopped off there. The reason I want to deal with p equal 1 by itself is because normally I wouldn't be able to divide by 1 minus p if p equals 1. Plug in, I get the limit as b goes to infinity of 1 over 1 minus p, just kind of stuck that out front. I have b to the 1 minus p minus 1. I want this limit to converge, and the only way for this to converge is if b is raised to a negative power. So 1 minus p must be negative, which means p must be less than 1. For all p less than 1, this integral will converge. Summations are very similar. They're closely related, so this means for all p less than 1, the summation as n goes from 1 to infinity of 1 over n to the p converges also. So let's look at some examples. Suppose I have the summation as n goes from 1 to infinity of n squared minus 1 over n cubed plus 1. In this case, the p is the difference between the degree of the bottom and the degree of the top. On the bottom, I have a 3. On the top, I have a 2. So 3 minus 2 is 1. My p equals 1, which means this sucker diverges. Over here, I have the square root of n to the 4th. Well, this is really 4 over 2, because remember the square root is the same thing as raising something to the 1/2. So the power on top is 2, and the power on the bottom is 5. 5 minus 2 is 3, so this converges. Summation as n goes from 1 to infinity of negative 1 to the n over n squared minus 1 over n squared plus 1. Oh, this is alternating. None of the others were alternating. That actually is going to make a difference. But in this case, it's moot because the terms don't go to 0. The limit of the terms is 1, so it will diverge. But let's say I've got something like this. The sum as n goes from 1 to infinity of negative 1 to the n squared minus 1 over n cubed plus 1. P is equal to 1, but we've got this alternating thing, which means every other term is negative, so the sequence of terms don't have to go to 0 as fast as if it wasn't alternating. The negative and the positives will do some canceling out. To show this, I need another test. Suppose we have this alternating series. For this to be an alternating series, my b sub n is positive, so that the negatives don't cancel each other out. The alternating series test says that if your terms are decreasing, so b sub n plus 1 is less than or equal to b sub n, and the terms are going to 0, then this alternating series will converge. Which means, in terms of my p test or my p series, if it's alternating, all I need is for p to be greater than 0, and it will converge. Look at this one again. It's alternating, the terms are decreasing, and the limit of the terms is 0. My p is equal to 1, therefore it converges. So let's check this out. The series is alternating, the terms are decreasing, and the limit of the terms is 0, so this converges. Now we're ready for power series. A power series is of the form summation as n goes from 0 to infinity of c sub n x to the n, which is that, where c sub n are constants called the coefficients of the series. This is a polynomial. This is an infinitely long polynomial. The question we have to answer is, for what values of x will the series converge? So first one, let's look at this. Summation as n goes from 0 to infinity of x to the n, which is just 1 plus x squared plus yada yada yada. So this is a geometric series. I know a geometric series converges when the absolute value of r is less than 1, which means my x has to be less than 1. Not only that, I can tell you what function this represents because we know the equation for the sum of a geometric series. The first term, 1, over 1 minus r, which in this case is x. So this function is equal to 1 over 1 minus x. Let's say we have the summation as n goes from 1 to infinity of n times x to the n. If x equals 1, that's not going to work because you can't add up n. That would be 1 plus 2 plus 3 plus 4. That's going to explode. If x is negative 1, well then we'll have the same thing but alternating. It's going to diverge. If x is bigger than 1, then we have a geometric series where my r is greater than 1, that will diverge. And if x is equal to, say, 1/2, well, that will converge because you've got a geometric sequence that's multiplied by n. That n's not going to affect it enough to make it diverge. Now, what I just did was kind of touchy-feely. We need something a little bit more rigorous because this is mathematics. So we're going to look at something called the ratio test. The ratio test. Consider the series n goes from 1 to infinity of a sub n. We're going to look at the limit as n goes to infinity of a sub n plus 1 over a sub n, the ratio of the terms, hence the name ratio test. Given that the limit is L, if L is less than 1, the series converges. If L is greater than 1, the series diverges. If L equals 1, you know nothing. So let's revisit the summation from 1 to infinity of n times x to the n. I have to look at the limit as n goes to infinity of n plus 1 times x to the n plus 1 all over n times x to the n. As n goes to infinity, n plus 1 over n goes to 1. Looking at my x's, I've got x to the n plus 1 on top and x to the n on bottom, which means all but one x cancels. I'm left with just an x on top. So cleaning this mess up, I'm left with just the limit as n goes to infinity of the absolute value of x, which is just the absolute value of x. Now, since the limit has to be less than 1 for the series to converge, that means the absolute value of x has to be less than 1. Let's look at another one. Suppose I have summation as n goes from 0 to infinity of x to the n over n factorial. So I want to look at the ratio of the terms. So I'll have a mess. I have got x to the n plus 1 over n plus 1 factorial all over x to the n over n factorial. I hate double-decker fractions. Since I'm dividing by x to the n over n factorial, I can switch that and multiply by its flip. Much prettier. So I've got the limit as n goes to infinity, x to the n plus 1 over x to the n. I've got n factorial on top, n plus 1 factorial on bottom. The factorials will cancel, and I'm just left with n plus 1 on bottom. I have an extra x on top, so x to the n will cancel, leaving a single x on top. Rewriting this, I've got n goes to infinity of x over n plus 1. Now as n goes to infinity, n plus 1 goes to infinity, and 1 over infinity is 0. 0 is always less than 1, so this is true for all real numbers x. So when we're determining what x's work for our power series, we can look at it. We can determine if it's a geometric series, or we can use the ratio test to figure out what x's work. So what are our takeaways? If the terms of a series don't go to 0, the series must diverge. If we think of p as the difference between the degrees, then a non-alternating series with p greater than 1 will converge, and an alternating series with p greater than 0 will converge. Now this only works when you don't have powers of numbers. This is when you've got a polynomial or a root over a polynomial of a root. No n factorial, n to the n, any weird shit like that. And lastly, a power series is an infinite polynomial, and our job is to find out what x's work in the power series, i.e. what will give us a convergent series.